Similarly,
So this is
students,
the
we can
operator
define
definition.
forward,
Now,
backward. The point
but
is
here, what that do? It tries to compute some differences. And how do we do that forward difference operator? It is quite simple. So the idea is like that. So let's say again there is a data set x0, x1, x2, similarly y0, y1, y2, and so on, and we know that all x values are at a distance of h. Again repeating, only x values, y values are not, because if y values are at a distance, and then we don't need to bother for the operators, because we know that wherever the values lies, so at a distance of h units, they are at a distance of h units. So what is the definition of forward difference operator? First, let's understand is symbol. We use a symbol delta for it, not e. This time we use a symbol delta. So whenever this delta applied over a function, whenever you find this delta is operator is applying on a function, it has a predefined definition in it, and the definition is, as you can see in its name as well, it's called forward difference operator. So it will compute the difference in a forward direction. So we have to apply. So for example, if I'm applying it on a x value, x could be x0, x1, x2 until any value. So according to its definition, you have to compute its difference from its forward value, that is a value which is lying ahead of it. So if it is x, then the forward value of the function is x plus h minus the value at which you want to apply the operator. So I want to apply the f of x forward. So what I have to do, I have to just compute the forward difference. One can clearly see it is just like a derivative. I computed a change between the two values. For example, if I apply a forward operator at x naught, so what I have to do, I have to look for the value that is ahead of it. So this is x naught, but it's not x naught, is f of x naught. So f of x naught is y naught. So keep in mind, we always do calculation in y variable, that is dependent variable. So y naught, and the forward value of the y naught is y1. So we will get f of x naught plus h minus f of x naught. So which means del of y naught, that is a forward difference operator applied at y naught, is equal to y1 minus y naught. Simple. So this is the definition of the operator which I am highlighting with the box. And the other thing is just a calculation. So what you do, you just need to compute the difference. If I apply a forward difference operator, that is a delta operator on y1, so what I have to do, I have to look which value is ahead of it. I have to compute the difference, y2 minus y1. Simple. For example, delta of y1 is nothing, y2 minus y1. Simple. So this is the operator, but it is a forward, so it means that we have to compute derivative of the value which is ahead of it. So from where we can clearly conclude we cannot apply this on the last value. I have not wrote down the last value, but so if I want to apply the forward difference operator on last value, is not possible. I hope you understand what this means, because I cannot apply here, because if I apply a last value, so I cannot find any value ahead of it because I go outside the data, so I cannot apply this operator there. So this is only for the forward. It's very simple definition. Now the interesting part is, which we really like, is to express operators in terms of others. So definition is quite simple, and in later stage we will know how we will use it, but at the moment this is the definition. But the interesting part or some conceptual part is to know how the operators are connected with this. So far we have discussed shift operator, that is E, and del operator, forward difference operator. So how these two are connected? So if you look this definition carefully, this one I am talking about, del f of x, this is definition, basic definition. So you can clearly see there is a del f of x plus h minus f of x. So what I can do, if I write down this thing again in a compile form, del f of x, that is a forward shift operator, equal to value at the at forward value minus the value of this function. And why we are subtract, you know, that is the word difference in the operator. So if you focus on this term carefully, we have discussed similar value in the last lecture as well, I mean last slide. If you remember this part here, oh sorry, one more slide. If you see this value, you have you can connect it. Remember, shift operator, if applied on any function, so it is equal to f of x plus h. We are having similar term in the forward difference operator as well. So in place of f of x plus h, I can write down e f of x as well. So here in place of f of x plus h, I can write down e f of x because they are similar. So in this way we can manage to connect forward difference operator and the shift operator. So what we have now, e f of x. Keep in mind, I replaces only in place of this term, rest is similar, minus, because they are numerically equivalent, represent same thing. Now what will happen with this? So we can see we have f of x, f of x, f of x everywhere. So but this equation is clearly telling us how the shift operator, forward difference operator are connected. But before to find that relation, let's introduce one more term. Del, in fact I will write down directly in an equation and explain to you. Or one can consider it as one more operator we are introducing, minus I, or sometimes people prefer to write down this 1 as well. I introduce something called I operator. In fact it's not I operator, we call it identity operator. So let's consider this portion as a rough. So what does identity operator do? It's nothing, it's just like multiplying a function by a 1. So if I apply a identity operator on any function, I will get back that function, nothing changes, in other words. So it is similar to say I have multiplied the function by 1. Understand? So this is just a rough point. Identity operator is nothing, it's just an operator. If you operate it over any function, you will get that function back. So just to have a operator with all the terms, I introduce this I here. I is an identity operator. But we write down this is identity operator. Okay, so every term has an operator. So what does this say? So if you apply a shift forward difference operator on any function f of x is equal to, which means you do not need to apply forward difference operator, you can compute same result based on this equation because it's equal to that. What you have to do, you have to apply a shift operator, forward shift on that function, and subtract that value with the identity operator, which means just subtract the value from that function. We will get the same thing as of the forward difference operator. So what we have now, we have a conclusion, just remove all f of x. So what we get here, a forward difference operator, in terms of operator we will get forward difference operator is equal to shift operator minus identity operator. So if you apply f of x here, f of x here, so you can multiply, you will get the same. So if you type f of x here and f of x here, so you can get the same result as out above. But I just need a relation between the operators. So I can say this is the relation exists between the forward difference operator and the shift operator. Sometimes in books you can find instead of I it is written 1 here, because I told you identity operator works just like multiplying it with the 1 positive 1. So that's not something to be confused about. A del forward difference operator is equal to shift operator minus identity operator. This is what you have to keep. So the only boxes are important. This is the definition of the forward difference operator, and this is the relation with the shift operator. Okay, if you are still confused where f of x going, it is the operator. So I just skip one step because that's the operator and I want to apply it on a function. So if I want to apply this operator, I have to put f of x here and I have to put f of x here, and then we multiply this, we will get the same equation there. So whatever this equation is showing, it is just a relation between the operators, not applying to the function. Okay, so this is the relation between the forward difference operator and the shift operator. I hope you understand the main point that we have discussed here. So if this is all clear to you, let's introduce one more operator, and that's we usually use. In fact, it's not a new operator, it is similar operator, but it has some other definition as well. Now student, why we have to introduce other operator, reason is, if you look carefully, to apply forward difference, in fact the word forward is quite clear. What I'm going to say now, the forward operator means I want to apply a shift in the forward direction. So we know that we cannot apply shift on the last value, which means we cannot compute the forward difference of the last value because there is no value lying outside the data. So what should we do in this case? We cannot compute forward difference operator as well of the last value. Keep in mind, when there is a forward word or forward movement exists, we cannot perform this on the last value. But however, we can do it on a first value. So in order to mitigate this problem, we define another operator in other direction, and we call it backward difference operator. We call it backward difference operator. And the symbol that we use is called inverted delta, or sometimes we call it nabla. Inverted delta or nabla. Inverted delta is very easy. So what is the definition? I'm not going to write everything again. So there is some function, you all know what does this mean. So, and I want to apply this operator. So if I apply f of x again on a certain function, so it has some values which is lying forward and a backward. So the definition of this function says you have to subtract this value from its backward reading. So the value is f of x, and you have to subtract it from its backward value. So now see student, this is the new part. Here I have used x minus h, which means if I am at, in fact if I am at a value x, then if I subtract h amount from x, I will go back of that value, back side of this value. So for example, if there is x0, x1, x2 till x3 and last xn, so what will happen, in this case, if I apply the backward on x2, I will go to x1, x3 I will go to x2, and so on. So this is the condition. So I have to go to the backward direction. So I can say x, if this is x2, we know that it is, if I subtract h amount from x2, I will get x1. So this is what is represented here. It is just a forward backward shift which already discussed. So and correspondingly we have y0, y1, y2, y3. There is no dot here, and till yn. Okay, so this is the definition of this operator. So let's discuss in the data set. If I apply it, for example, if I apply backward shift at y2, so backward shift of y2 means I have to subtract this value, that is y2, from is the value that is on the back side of it. So what is the value on the back side? Just one step back is y1. This is very simple definition, just like a backward difference operator. But what advantage we have? So we have this advantage. If I apply this operator on the last value, that is yn, this value, so this value, so I can still compute the backward difference operator, because the yn is the value, subtract yn minus 1. Now question is, what is yn minus 1? One can clearly understand it is the second last value somewhere there, yn minus 1 corresponding to xn minus 1. It's the second last value. So I can apply this operator, but I cannot apply the backward difference operator on the first value, because there is no value exist at the first data set, beyond the first data set. So this is the reason behind we have defined the difference operator in a forward movement and the backward movement as well. So one can clearly see that these are also something close to the derivative as well. If I divide this by h, similarly on the back operator, if I divide this quantity by h, and h is very small, that they can represent as a derivative quantity as well. I hope this is understood. That similar to the last step, what I do, I also try to connect shift operator with the backward difference operator. So what is the relation between the shift operator and backward difference operator, Nabla? So one can clearly see based, okay, I have to highlight this part as well. This is the definition that you have to remember. Subtract from the value which is on the back side behind. So E of this is a shift operator. Symbol of a shift operator is E, but we have to see how we can connect it. The one can clearly see, which I already introduced, that we can shift forward and we can shift backward as well. So f of x minus f of x minus h, this is written here. So this is the definition of backward difference operator. Now how do we apply it? Del f of x equal to f of x, and I can write this f of x again as a identity operator. So if I write it down like I of f of x, I hope you all understand, it will not impact anything. Minus, now this is interesting, I can write down this whole f of x minus h as this term, e minus 1 of f of x, e minus 1 of f of x, because you remember I said if you put any power on the shift operator, let's go back here, so it will move that quantity to that amount. So if you look this example, so if I apply e minus 1 on y2, it will move back towards the y1. So this means that this power is important, and negative sign represent negative. So what we are doing here, fx minus h is a value which lies just behind the f of x. So what I am doing, I am applying a backward shift operator of 1 unit. How much unit? 1 unit, complete 1 h, shifting from f of x to f of x minus h. So if you apply this operator there, you will get this value. It's the same thing. So both are similar notations. And similarly, if you understand that in the last step I replace a relation without any function, so I will get a shift operator is equal to identity operator minus E inverse or shifted one. So this is the relation between shift operator, which is obviously a backward shift operator, and the backward difference operator mainly. Although it contains identity operator as well, but that's not what we want to compute or aim to compute. I hope that that's clear to you all, and this will help you to understand some basic concepts that we have to, because this is just a building. I already told you this is a building block information. We need some formulas so that we will use it and the further calculation. So what we have now, we have this relation. Listen, the relation that I have developed here is shows the relation between the backward and the shift operator. But sometimes this relation is also modified to obtain some other relation. Like this is the relation we have just derived, that shift operator minus identity operator minus shift operator. Backward difference operator is linked with the forward shift. What we can do from this relation, we can connect all the relations in a one equation, like shift, forward and backward in one relation. I think equation or relation. How? Let's start from this. So if I start from this equation, we have a backward operator is equal to identity minus shift. This is in the case of shift operator, you can consider them as a power as well. So E is negative half. This is the condition we have. So what we can do in this case is that we can apply this relation in the form of E inverse. In fact, saying inverse is not good. Let's do it other way. Let's say if I multiply this operator throughout by E operator, identity operator. So what will happen? Operate with E forward shift operator in E operator. Operate with E. So I have to apply E on both sides. E inverse of I. So if I operate it, because a linear operator, E of I minus shift of shift. So one can clearly see that shift operator is applying on an identity operator. So identity means nothing. I mean it will not change anything. So the only thing that will left is E. So basically whatever be the function is here is only changed or modified due to E, not with I, because I is just an identity operator. It will keep the function same. So what I can do, instead of I can write down E only, or in other words you can memorize that, or you can remember that whenever there is an operator and there is identity operator, then identity operator is useless. The main operator will perform their duty. Minus is just minus, like that. And one can clearly see, if you have, if you want to shift anything, let's do it some little bit rough work. So if you have this function and you applied a backward shift, so you will get f of x minus h. This is h. Okay, but if you apply again E on it, E operator on it, so you have to apply on both sides. So when you apply E, what does this mean? You have to move it forward. So moving forward means you have to add h in it. So what you get? F of, you are at f of x minus h, and you have to move forward by plus h. So this will cancel out, and you will end up again at f of x. So this means that if you apply E on E inverse f of x, so they operate just like an inverse to each other. You will come back to that function again. It's just like that, there is no operator is applied. So what we can do, we can say E and E inverse will cancel out each other, and the only thing left is identity, like the one left. One means identity in our case. So what we have here, we have what we have here is E backward shift operator is equal to E minus identity operator, but I do not want to write down here. Let's go back in our lecture and try to find out what does E minus I operator is equal to. Let's go back. You can find something here. So if you look in this relation, this says E minus I, that is shift operator, forward shift operator minus identity operator, is basically equal to the forward difference operator. That's interesting. So E minus I is equal to the forward difference operator. So E minus I, which is in this case equal to E times of nabla I, is equal to the forward difference operator. So what I can do, I can simply put here forward difference operator. So this is very interesting equation. In this equation I have connected shift operator, which is here, forward operator, which is here, and backward operator, which is here. So all three of them are connected in a single equation that represents how the shift and forward and backward works. So what does this equation say? This says if you apply a forward on any function, is it exactly the same if you apply backward to that function and then shift it forward? Interesting. For example, let me write down. In fact, this needs explanation. E backward is equal to forward. This is the relation that we obtained. Shift forward and backward in a one equation. So what does this say? It says if you want to apply a forward on a function f of x. So this process, this step is same as if you first apply backward on f of x, and whatever the result you get, you should apply a shift on it. So they are same. Let's verify this. So keep E as it is. So backward of f of x, you have to memorize a function will subtract it from f of x minus h, a previous value. Whatever is the value will be subtracted from the previous value. And now apply the shift operator on each value. So it will shift it E f of x minus E f of x minus h. So if I apply shift on any function, we know that it is a forward shift, so it will be equal to f of x plus h minus, and if you shift forward a value, you will get f of x. You can try by adding plus h, you will get the same, is equal to what? Del f of x or not? You can see that is the same or definition of the forward difference that we develop on this part, the same definition. So what does operator says? If you want to apply a forward difference operator, you can do it one way as well, that you first apply a backward difference and then shift it forward 1 unit, so you will get the same result. That is just a proof of it. We can develop or get different relations from this as well. For example, the other relation that I can derive by shifting E on both sides is that the backward difference operator is equal to E inverse of forward. What does this? I just shift this E on this side, shift operator on this side, so it will become the inverse operator. Yes, it treated as a power. So this is another relation deduced from it. So what does it say? If you want to apply backward difference operator, So don't do it. Just shift the data with forward operator and then shift one unit back by applying the backward shift operator. You will get the same result. Same result. So this is just a relation. So student, let's stop the lecture here, whatever the time we have, and focus on these points. Try to understand the points based on this concept. It is basically not it is not that difficult. We have not done any calculation yet. We just defined some operators and their definitions and their relation between them. Although this is a building block information, we have to use them in a further topic, but this is the information you should remember. Okay student, so these are the some points. Just to summarize them, we have some operators there: backward, forward, and shift operator. Operators are just a process that has a symbol defined on it and we have to apply them. Before that, we covered some examples related to the errors, multiple function error, single function, which this topic is linked with the first lecture as well. So here the lecture is started with operator. It will continue in the next lecture as well, and then we will hope to continue further. So this is the lecture number 2 in our sequence, but this lecture